Okay, we're sorry.
Oh.
Okay, let's get started. It's my pleasure to introduce my colleague, Dr. Carole Hayakawa. Carole did her undergraduate degree at UC Berkeley, trained formally as a mathematician, and then went on to UCLA and got a master's degree in applied math. Went out to industry in Southern California, mostly working in military related applications. I think she got tired about having to lie to people at parties, what she actually did for a living, given her classified work. And so then that prompted her to go back to grad school, where she went to Claremont Graduate University out in Claremont, about an hour or so from here, to pursue a doctoral degree in applied mathematics, where she met her mentor, Professor Jerry Spanier, who's one of the pioneers of the Monte Carlo method, and proceeded to specialize in that for her graduate work. Jerry, at around the time that Carole joined his group, started a collaboration here at the Beckman Laser Institute. There are a number of people from Claremont, interacting with us here, and that's when I first got to know Jerry, and then soon after met Carole as a PhD student, and I was also a postdoc initially, and then started my faculty position. We started a collaboration that lasted at last to this day. And Jerry sadly passed away a year or two ago, at the ripe age of what, he was 96, something like that. And Jerry was incredibly active until almost his final years. And so Jerry and I actually, and Carole and others, first formulated the initial set of short courses. And so his legacy really lives on through this. And so Carole and I have been working continuously since then, and she's going to continue our theme of Monte Carlo in this second lecture of the morning. So thank you, Carole. Let's welcome her.
Thanks, Awesome. So I'll be describing some Monte Carlo methods, extensions, and applications. Just a outline, I'll go over traditional Monte Carlo concepts, describe perturbation and differential Monte Carlo and how we form those estimators. I'll also describe spatial frequency domain estimation estimator and temporal frequency domain. I added in some charts on fluorescence because I saw that people were working on that in this group. And at the end, I'll show you how to set up a Monte Carlo simulation and what options are available with using our code. So I have this roadmap here that describes the process how we go from the analytical model to the probability model. And this roadmap is used later in the talk for other applications. So I wanted to kind of lay it out here. We start with the integral differential. I'll use this little hand. Integral differential RTE, which describes radiance as a function of position, volt-r, and omega. Omega is that theta phi that Scott talked about. So we start with the integral differential RTE, and we transform it to the integral form of the RTE. Completely equivalent. We use the method of characteristics. I'll show more about that later. And now we have something that describes the collision density. That's psi, the psi equation here, psi function. From there, we define a probability model. We have a random variable C, and this estimator, along with a detector function F, is going to allow us to estimate or predict measurements. Often we're running simulations to see what would happen when you're actually measuring something. So I'll show how that evolves. And if you define this estimator in terms of the components of the integral RTE, then you ensure that the random variable is going to solve the RTE. That's important. You want to make sure that you're running something that is solving the RTE. So here is the integral, time-independent integral differential RTE. You've seen this before. We've got radians here, omega here. We've got the phase function here, mu s, scattering, mu t, total attenuation here, where mu a plus mu s equals mu t. And why wouldn't you just solve this? Well, it's hard to solve analytically. There's only very simple, like a bidirectional problem that you can set up, simplifies the equation that can be solved analytically. So in its current state, it's a difficult equation to solve. So that's what drove Jerry Spanier and Eli Gelbard back in '69 to transform this equation to the integral form. And the reason why they did it is for two important reasons: to show that the existence and uniqueness of the solution is there, and also to represent the solution as a convergent infinite series. That's important too. So we use the method of characteristics. So if you're in a partial differential equations class, possibly you've seen this, where say you have a function of two variables, you have a PDE describing it, you parameterize one of the variables such that it's constant along these characteristics. It reduces the dimensionality of the problem, reduces it to an ordinary differential equation, and then that's solvable using integrating factor like Scott talked about. So we use that method of characteristics, and actually Bell and Gladstone lays out all the nice details. If you are interested in that, they give all the details to how to transform the integral differential equation to this integral equation, where psi is the collision density. It's related to the radiance by a factor mu t. Okay, we have this thing I call fancy K. It's an integral operator. It looks like this equation here. It's an integral of plane K and psi. And then you have this S over here, which is the density of first collisions. So in this operator, there's a K, which is comprised of two components. And the first component is the collision kernel, C. C is you're sitting at a position R that's fixed, and C kernel allows you to determine if you're going to scatter. So this probability mu s over mu t is the probability of scattering. So you roll the dice and you figure out, did you scatter? If you scattered, then you use the phase function to determine which you're going from omega prime to omega, how you're deflecting. The T part of K is this transport kernel, and Scott presented this too. This is in its full glory because it allows for mu t to change along the path. So now we're in a fixed direction, and we're figuring out, we're at r prime, how far are we moving in this fixed direction? And it's given by this equation. This integral allows for mu t to change along that path, so full heterogeneity. But if it's homogeneous, then it reduces to a very simple mu t e to the minus mu t distance traveled. Okay, and just to finish the equation, S represents the density of first collisions. You can see that it has a Q, which is in the integral differential equation, but it's been transported to its first collision using T, the T kernel. So if you see a simulation, this is a schematic of what's happening. You have the source, you transport it using that T kernel to the first collision. At that first collision, you could scatter, or you could get absorbed. This is a little symbol I use for that it got absorbed into the tissue, and it's dead. Then you move on to the next photon. Here, you figure out okay, it did scatter. This is the probability we use for that. We determine the angular change using this phase function from omega prime to omega. And then we use t to determine how far we go. Okay, so these elements, C, T, and S, are elements of the random walk. We call the movement through the tissue of the photon the random walk. And these three functions are describing how it moves. One of the key benefits of writing transforming the RTE into the integral form, integral differential to the integral, is that you can write it as a convergent infinite series, the solution as an infinite series. So if you rearrange terms, so it was C equals fancy K C plus S, you can bring everything to the left-hand side like this. And if you remember from series in calculus, that if you had 1 minus x, 1 over 1 minus x, you could expand it into a series of 1 plus x squared plus x cubed, as long as the absolute value of x is less than 1. Same sort of thing here. As long as the norm of this operator is less than 1, you can expand it like this. And so this first term is S, the identity with S, then the fancy K, S, K squared S. So these are this is called the Neumann series, and these are the components that determine the collision density at a position R and a direction omega. So if that's this position and this direction, you would capture all the photons coming directly from the source. So the source would have to be directly behind it, like in a transmission situation, and scatter straight in, have its first scattering event into this location and direction. So that's this term. Or you could scatter once and go into that direction. You could scatter twice, and that's these components of this just being expanded out into details. If you take it to infinity, you have this infinite series, and this infinite series is guaranteed to converge as long as this norm is less than 1. So now we have the global solution. We have psi as a global solution, but we're really interested in a measurement. And the measurement needs a detector function. So we define a detector function, f, integrate the global solution with this detector function to give us a measurement of I. Notate a measurement I as I. So I'll give you an example. So for instance, with respect to reflectance, this would be the detector function, F, R, and omega. Basically, what this is saying is we want to capture everything, like in this picture. Say we have a fiber that has some finite extent, so a surface area that the photons could exit, and maybe it has an NA that you want to, can only capture the photons within some sort of angular cone. This chi function says, okay, if the photon comes through and happens to come out that particular spatial location and the NA, then we're just going to say 1, like Talia. And if it came out other places or not outside this cone, we're not tallying it. So it's just basically a way to ping, yes, we're tallying this photon, not. A way to segregate all the photons that would mimic a measurement. So that's the analytical side of the problem. Now we have to define a random variable that defines the method of tallying. And there's kind of two parallel worlds going on, the analytical world and the probability world, but they're very closely related, it's just slightly different definitions. So if we define this random variable in terms of the RTE components, the S, density of first collisions, the K, which is comprised of the C kernel and the T kernel, collision kernel and transport kernel, we have a detector function. There's potential weights that might evolve in this estimator. I'll show you what happens there. And the probability representation of the measurement is that we're evaluating this random variable with a measure. Okay, just think of the measure being the probability density functions that compose the S and K. So those are pretty simple functions. That's just the way of evaluating this integral in terms of measure. And if we get the expected value with respect to that measure, which is launching n photons and then getting the mean value of that estimator, we will get a measurement of a prediction of the measurement we're trying to model. So let's look at a particular example. We're looking at reflectance here. I have simplified the position and omega to be just called P. So P1, P2, P3, P3 are locations and directions that the photon has scattered at. And then I create something called a pseudo collision, because if the photon is at P3 and transports, it's usually transporting beyond, into the air here, but we intercept it right here where that detector is, and put what we call a pseudo collision, and put a marker there that says, okay, at that point, that's where we want to capture information regarding how detection is done. So for reflectance, we use something called this modified terminal estimator right here. And it looks kind of complicated, but basically it's ratios of the analytic versions of these functions, with the denominator being the measure of these functions. So analytic form, probabilistic form, analytic form, and a detector function. And the detector is at this pseudo collision. Okay. So just to describe a random walk process, this is a set of functions that describes how photons are initiated, how they move from collision to collision, and then how they get terminated. And this subscript M here designates the measure that's used to run the random walk. And I think that some of this where the evaluation of the estimator with respect to this measure gives a representation of the measurement. Okay, key thing though is if you alter the random walk process, then the estimator needs to be altered appropriately with weight modifications. Otherwise, you won't be solving the RTE anymore. That's what the term unbiased means. It's that you are not adding any bias into your simulation and that you will solve the RTE. So I'll show you how that's done. So I'm going to start with something called the analog random walk process. This is the very first random walk process that was historically run, back at Los Alamos, where they said, you know what, let's just define the probability model, be exactly what the analytical model is. That makes sense. Makes things simple. Let's make sure that how we sample the density of first collisions is exactly what the analytic form of the equation RTE says. And let's make the movement between the collisions exactly the way that the equation says. We're now sampling the distances with mu t, e to the minus mu t distances traveled. Because of that, using that transport kernel, our mean free path between collisions is 1 over mu t. And because we took this simple form, all of these factors in this complicated equation reduce to 1. And basically, you're telling 1 if the photon exits the detector and 0 otherwise. So it's a binomial estimating. Really nice. So in this case, the photon comes in with weight 1. There is a probability and transports. There is a probability that it could get absorbed and it goes away. Then we start with another photon. If it does scatter, we keep on going. It retains its weight 1. And if it happens to go out the detector, then we get to score 1. So after running n photons, we tally how many ones went out the detector, divide that by n. That's our estimate of reflectance at that location and direction. Okay, but you can imagine with analog, if you have a highly absorbing tissue and your detector is really far from the source, that few photons, most of the time they're going to get absorbed, or after a few collisions, they're going to get absorbed, and many won't make it out this detector far away. So two methods were designed: discrete absorption weighting, and you'll see in subsequent continuous absorption weighting. Discrete absorption weighting is commonly used in most Monte Carlo codes. Jacques and Wang, first MCML code, used discrete absorption weighting. It is an alternate way to account for absorption. Okay, so the way it works is that you disallow absorption of the photon, but you can't just do that and say, yeah, we're just gonna move them along. You have to accommodate that change in the weight of the photon. And through these definitions of how the random walk runs, 20 and 21, these in this equation for the estimator, these cancel to be mu s over mu t at the position that the collision happens. So the photon comes in with weight 1. At this first collision, its weight is going to be degraded by mu s over mu t at that location, whatever that, if this is heterogeneous, where that location is. So that's why this is kind of a solid red, meaning the weight stays 1. It degrades to mu s over mu t, then transports, and the transport is the mu t e to the minus mu t distance traveled. Then it'll be hit by another mu s over mu t. This is showing a homogeneous situation. And by the time it exits the photon, if it exits the photon, the weight will be mu s over mu t to the power k, k being the number of collisions it experienced prior to detection. If it didn't go out the detector, then nothing is scored. Okay, another method to disallow absorption but account for it in a different way is continuous absorption weighting. Here, though, we're actually transporting with respect to mu s e to the minus mu s distance traveled. So the mean free path between collisions is 1 over mu s. And defining the random walk process in terms of this s and k, we now cancel and get these terms, and I've written them such that the mu a could vary along these paths. So you start the photon here, it goes the distance d1, and I tried to shade it because the weight is continuously being degraded along this path according to e to the minus mu a, if this is homogeneous, e to the minus mu a distance traveled. And then, of course, we figure out what direction it scatters, but we're not going to absorb. And then we move again, and this distance is going to add to that Beer's law, and until at the very end, we have gone a total path length of L, and the weight that gets tallied is e to the minus mu a L, L being the total path length. So here is a series of simulations that show the difference between analog DAW and CAW for a US prime over mu a of 10. So I give the details here, G of 0.8, N of 1.4. I've got a L star of about 1 millimeter. And so let me show what this is. Oops. Oh. I'm going to stop it. Things work differently on the podium than here. I'll just let it run. So it's showing one photon, and then how these 3 estimators fill out fluence. And then I add a detector, and then I make photon bananas. But one of the things that, like that name, one of the things that I'm tracking here is the time. No, wait. Yeah, not working. Sorry. I tried to actually change this to a Windows compatible video, but Linux and Windows don't like to get along. So let me just roll it again, but I'm keeping track of time. You'll see here. So you can see that analog is taking way less time. And you can see also that analog is not filling out the depth of this fluence map as deeply as DAW and CAW does. That's because it's actually absorbed, the photons are getting absorbed, whereas DAW and CAW, they're running until, and they're tallying, contributing to the tally along the way. Oops. Okay. So just a chart to describe the pros and cons of each method. Analog runs really fast, but tallies away from the source can be difficult. But the theoretical analysis is straightforward. DAW and CAW, you can tally far away from the source. One of the things that's nice about DAW is that you tally at the collision point. Okay, so so no path length information is needed. The photons do run, so if you have a semi-infinite media, the photons run until they come out the surface. And maybe they're spending a lot of time in areas that you're not interested in, and can take a lot of time. CAW, again, tallies away from the source possible. It captures path length. So if you have a very thin layer in your system, it's going to tally if you scatter across it. So maybe you scattered here and here, there's going to be a certain path length that goes through this thin region, and you'll be able to contribute to the tally of, say, fluence or radiance in this thin region, whereas DAW, you actually have to scatter there in order to tally. But because it's doing that, if you have a very complex tissue domain, then you have to figure out all the particular path lengths, like in tetrahedrons. Oh, I entered a tetrahedron, I went halfway through to this other side, but then I went to this other tetrahedron. You have to keep track of all those path lengths. CAW is often used in a lot of codes because it uses Beer's law. So you can run a series of photons. You can say, gee, I want to change the absorption in the tissue. You can determine it very fast using Beer's law, and that's why people are drawn to CAW. Now, a way to compare, why would you use one of these over the other? We use something called efficiency. And efficiency is 1 over the relative error squared times time. Relative error is the standard deviation divided by the mean. And we use this metric to compare the different methods. Okay, I'm going to change topics. Any questions so far? Okay.
Well, can you unpack the computational efficiency metric a little bit more? Just try to elucidate
Yes,
why it's constructed the way it is.
it's a
and-
non-dimensional metric. If you can think, okay, so one of the metrics, or one of the things that describe Monte Carlo, is that the variance decreases as 1 over n being the number of photons launched. More photons you launch, it's going to reduce the variance. Okay, the relative error is the square root of the variance. Okay, so when we square the relative error here, that's going as 1 over n, and the time is kind of going as n. You know, each photon is going to take average amount of time, same amount of time. So this creates a non-dimensional metric here. And it's helpful to know the efficiency, because you could run, I mean, this is what I just was having a conversation with Tim earlier about how, gee, I'm running this and it's running so slowly. It takes me 5 hours to get this result. So time is a big factor to people running Monte Carlo. But you can't just do it on time. You have to make sure that that you're reducing with that added time, you know, you're gaining with it. So yeah, I would say that the biggest complaint of somebody running Monte Carlo is, yeah, I have to wait for the results. So yeah.
To amplify, right? So time basically scales with the number of photons, but the different methods don't necessarily give you the same relative error for the same number of photons.
For sure.
So even though analog runs really fast, you can run 1,000 photons much faster in analog than you can in CAW. But as you'll see this afternoon, the relative error you get from that result is typically much higher than the relative error you get from DAW and CAW. And DAW and CAW generally are roughly equivalent, but there's certain situations where CAW is better than DAW.
Yeah. Pros and cons.
Right. So this efficiency is helpful because you want a large number, right? You either want the relative error to be small or you want the time to be small. That gives you a larger number.
Yeah.
But if the time is small and the relative error is large, well,
Yeah.
that's not so great. So it's kind of a way to wait, you know, is the time worthwhile given the quality of the result?
We actually have a switch in our code that allows you to choose analog DAW and CAW, but most of the codes out there are doing one or they're typically doing DAW or CAW. And I don't know if they necessarily say that outright. You kind of have to go into the code and see how they're sampling their transport, and then you'll know which method they're using.
The standard deviation and the relative error equation, is that from like running the simulation
Yes.
multiple times?
Yes, you can. So if you've taken statistics, you know that the mean is the first moment. We tally the second moment too. So we take so as the estimator, C is getting tallied. So say it tallies in analog, it's going to tally 1. And then we take the square of that tally and we tally it to the second moment. And if you have an estimate of the second moment and the first moment, you can generate variance from it.
Is that scaling with 1/n due to it being like a Poisson type, like number of, or where does that scaling come from for the 1/n of the variance? Does it comes from it's like a discretized like number of trials, or?
So I think what you're asking is, so the equation for variance has a 1/n in it. Yeah. And that's where that's, yeah. Okay. Does that make sense?
But I just want to make clear. So you don't have to run the Monte Carlo multiple times to figure out the standard deviation of the result. When you have a detector, you are tallying multiple photons, and the variance comes about from the variability of the photon weight at the detector of all of the photons that you detect. And the better the result, the smaller the variance of that population of photons is. The more photons you detect, the lower the variance becomes. So each Monte Carlo simulation and each detector gives you the mean estimate and a variance or an uncertainty associated with that estimate. Because remember, Monte Carlo is a stochastic method. The numbers you get are an estimate of the solution, and it has an uncertainty associated with that estimate.
But in theory, if n goes to infinity, their variance is 0, and you estimate it perfectly. Yeah. That's why Monte Carlo is the gold standard when running a solution to the RTE.
Yeah, sorry, perhaps you mentioned this and I couldn't hear, but how do the different efficiencies for the different methods compare in the sense that...
You'll see in lab.
okay.
That's a good question, thanks. You're like my lead-in to,
So in CAW, you said that you can, using Beer's law, you can take into account multiple mu A values, so that I guess that saves time instead of repeating the
For sure.
simulation.
yeah,
Can you do the same for mu S?
no,
No?
no. No, but, no, you can't, not in conventional Monte Carlo. We have something called scaled Monte Carlo, which I'll describe later. There is a way to account for MUS, but it's a different beast.
Mhm.
Yeah,
Thank you.
Other questions?
yeah, really good question. Thanks. So I'm shifting on to perturbation and differential Monte Carlo, just to give kind of inspiration as to why somebody might use something like this. It's used in diffuse optical tomography. I give a reference here where they are trying to reconstruct the mu A and mu S prime locations within. So here's on the first row is a phantom with a known mu A perturbation, known mu S perturbation location and extent. And using perturbation and differential Monte Carlo, this is their reconstruction of that back in 2005. Now, photoacoustic optical tomography also does it. Again, we have some sort of phantom and then its reconstruction here. Next week, there's a talk on photoacoustic optical tomography and first time for this course. So that's exciting. Okay, so the general problem is that you have some sort of tissue situation. It doesn't have to be homogeneous, but for simplicity, let's say it's homogeneous. And then there's this potentially cancerous region, a region that you're thinking, some sort of morphology is going to happen there, and I want to see if I'm going to capture it. Am I going to, with the setup of my source and detector, it's a good thing, these to know. If this change happens, am I really going to be able to detect it? So you have some sort of baseline situation in which you have a tissue system, and then you have a perturbed system in which there's a region where the optical properties, and I just listed them as alpha, so like mu A and mu S prime, could be G, and there's a change in this region. And now you want to know, what's the change to my measurement, if at all? Maybe you don't see any change due to these optical properties within this region here. So one way you could do it is you could run another simulation. You could run the baseline simulation, and then you could say, okay, changing the optical properties here, I'm going to run a separate simulation where I come in here, change optical properties, I scatter, move around here, come out here, change optical properties, come out here, and figure out what's detected. So that's one way to solve this. However, PMC will allow you to solve it based on the baseline set of random walks, and that has a lot of advantages. So the way we do this is that we take the healthy system, whatever it be, and we run a simulation, taking note of the number of collisions in this region that we're interested and the path lengths in this region. And we put that into a database, okay? And this could work for reflectance, fluence, radiance, all the different solution domains with respect to source detector separation, time, spatial frequency, temporal frequency, and would work for all of them. So let's just say we're getting reflectance here. And this is our plot of the healthy tissue. Okay, now to understand what that change would be due to changing the optical properties in here, we apply something called the radon-nicodine derivative. It takes the estimator and applies this ratio where mu hat is the perturbed measure and mu is the unperturbed. Okay, it sounds kind of complicated when you see the details, not so complicated, but what we're doing is we're applying a weight to the information that we have stored in this database in order to determine what is my Monte Carlo prediction of the measurement of, say reflectance due to this change. Okay, so, and it is unbiased, so it solves the RTE. And I'll show you how it's done. So let's say we're using DAW and we have this healthy tissue situation. We run the simulation, the baseline weights are W equals A. This is counting for specular, just a constant. And then we have this DAW factor, mu S over mu T, power K, K being the number of collisions the photon experienced prior to detection. Okay, and then we save in this simulation the path length in here and the number of collisions for each photon. Okay, so say we change mu A and mu S by this delta mu A and delta mu S. Then we have, this is the baseline weight I just showed you, and we apply this weight. Okay, this looks a lot like the ratio of C's, and it is. It's the ratio of that C, that first probability in the C kernel, US prime over mu T, US over mu T hats, or hats, divided by the baseline to the power J, J being the number of collisions in here. And then this looks a lot like the T kernel. I just simplified it. It's the hatted versions of mu TE, the minus mu T distance traveled, divided by the unhatted version of that. That's what this, S being the total distance traveled. So you just read that database, you go photon 1. What was J? What is S? Boom. I know what the estimator is telling. Tally that. Tally next one, next one, next one, next one. Atom, divide by number launched. You've got the reflectance. This is on a log scale of the baseline. I doubled absorption to show this dashed line, and then I halved absorption, and it shows this line. You can see the little wiggles are tracking each other, and that's actually a good thing because the results are correlated. That correlation is working in your benefit. So the extension of PMC leads to derivatives. And the derivatives, knowing the derivative of the measurement. So say you know the derivative of reflectance with respect to mu A or mu S. That's helpful. That's helpful information. You know now, how that measurement is changing when as UA is changing or as US is changing. And so that gives you sensitivity information. Also having the derivatives means that you could feed this information into a gradient-based optimization for finding the optimal change to this whatever optical properties changes you're looking for. So it helps you can actually use PMC and DMC within an inverse solver in a realistic way. Before it was kind of not heard of because every iteration of the inverse solver, you'd have to run a simulation. Now you can just read the database. Okay, here is my step in the inverse solver. These are the optical properties. Give me my prediction. And the estimation of the derivative of the estimator is the mean of the derivative, taking the derivative of the estimator. The derivative of the estimator is the estimate of the derivative, is the way to say it. And so given that, we just take the derivative of PMC here with respect to, say, mu A or mu S, straightforward derivative, and now we have an estimate of how that estimator is changing with respect to changes in these optical properties. So I show a plot of the derivative of reflectance with respect to mu A, and you can see this correlation. So the advantage is that you're saving time. You're not running a separate simulation that takes time. You're just reading a database. Something to compare is that I ran 1 million, took about 1,600 seconds, but reading the database took about 2.5 seconds. Another big advantage is that this correlation is capturing the change to the measurement due to just the change of the optical properties, not any statistical error that would be inserted if you ran a separate simulation, statistical error. Okay, so that's some of the advantages. Okay, I'm shifting again to how we estimate spatial frequency domain. Did somebody in here doing spatial frequency domain? Oh, should I wait until I go?
Because see if there are any questions on perturbation and differential Monte Carlo.
So just to clarify, perhaps, in both PMC and DMC, J stands as the number of collisions inside
The perturbed
the
region.
perturbed region, and
Yeah.
K keeps being the total number of
Yes.
collisions. Okay.
Yeah, yeah. And S is the path lengths in that perturbed region. I think I notated L as the total path.
Okay.
Yeah.
Okay. Perfect.
Okay.
Other questions?
Oh,
Can you explain the tumor part? It's a tumor, right, in the middle of the healthy tissue?
well, it's,
or-
it's an area where you think some sort of morphology is happening. You want to know,
Mhm.
is that, is the change to the optical properties are occurring? Yeah.
I just need a little bit of clarification on how that works. So when you're basically putting in new optical properties based on what you think that is supposed to be, like a tumor or whatever, you're not changing anything else from the healthy tissue.
No,
You're just
all-
adding the optical properties of the
Yeah,
new.
all these optical properties in the lighter pink
Mhm.
remain the same. You're only changing optical properties in the darker pink area.
Okay, so that's what you mean when you said that the change in the plot is based on the optical property, not the statistical estimate, right?
Yes, that's just due to the change that we perturb these optical properties in here and not due to the fact that we ran a different simulation. There's some statistical differences.
Okay,
Yeah,
thank you. I just needed
Yeah.
a clarification, that's all.
sure.
I also wanted a clarification on the same thing. So when you do this method, you're assuming that the walk is exactly the same? Or
Yes,
why can you assume that? Like that the path and is the same when the optical properties are different?
well, because so you can, let me go here. So you run based on, and for simplification, I just assume that this is homogeneous, but it could be heterogeneous. It just makes it a little complicated because you have to keep track of, the different, you might have changes to mu A and mu S spatially within, and that's allowable too. You just have to dissect this region into regions in which you keep track of the number of collisions and the path lengths in each. And so you run that simulation and store the information, and then you insert the fact that now we're going to change the optical properties. Now, we've done PMC with the whole domain being the perturbed region. That's fair. So it doesn't have to, I just kind of put it into a region here just because sometimes people are looking for changes in a particular region. They have some sort of geometry and tissue where they're pretty sure the rest of the system is solid, but some sort of change is happening in some area. So that's why I kind of,
So Carol, I think the question is this, is that in perturbation Monte Carlo, you're leveraging the photon trajectories in the original baseline simulation. But in reality, if you were going to run a second Monte Carlo simulation with the perturbed region, those trajectories would be different, presumably.
oh, is that, okay.
And so the question is that how can you get away with getting an assessment of the change in the measured signal using the trajectories from the sample where the perturbation wasn't there?
Yeah. That's this radon-nicodine derivative. It allows you to reweight the photon trajectories. Oh, kind of dim. Yeah, this radon-nicodine allows you to, I didn't really kind of go over the details of this. So you're looking for the change to the measurement, and you could define the estimator to be that two-region estimator where you actually change your random walks. But instead, you use the way you ran the random walks from the baseline situation, but apply a measure to the baseline estimator, and it allows you to evaluate that change to the measurement based on that. So yeah, the magic happens with this radanicodine, and this is actually proven to be unbiased when you do this. So
So Carol, maybe can I offer an explanation that's not as general and as elegant as yours, which is very comprehensive? So
sure.
go to the next slide. I want to kind of maybe the next one after that. Maybe I can unpack this a little bit because I think the form of this equation for the perturbed weight kind of gives insight into your very good suspicion. So this transport correction, what it's saying, well, in the original simulation, we looked at loss of light due to the fact that your probability of interaction with the medium along a path is proportional to, in the original situation, to mu t exponential to the minus mu t times the path length. Well, but in this new situation, the mu t is not mu t, it's mu t hat. So let me get rid of the probability that I assumed in the original situation and substitute it with the transport happening in this situation. So that's one thing. Handling this gives a very good approximation for the loss of light due to the new optical properties relative to the old optical properties. Then the other thing, which I think really hits your concern, is that, well, the photon trajectories are different. And that's right. Because in the original situation, you estimated path lengths based on a mean transport mean free path based on the, and that's where you get the path length. You choose your path lengths, and that's what this term does. In the original, you assumed a path length and a loss based on the mu s exponential. Yeah, I'm sorry, mu s over mu t exponential to the minus mu t, and you do that on every collision. So you get rid of that and you substitute it with the new one. So this basically does a reasonable job at looking at the loss of light. And this basically deals with the fact that your trajectories are slightly different. You have to expand or contract these individual path lengths. So it's not perfect when you have large perturbations, but for small changes, that's why it's perturbation Monte Carlo.
That's right.
You're just perturbing a little bit, it gives you a pretty accurate result. So not as general as but you can apply this concept to much more complicated problems. Then when you do that, you have to go back to the probability theory and do the radon-nicodine formulation.
Yeah.
Yeah. Is that fair, Carol?
Yeah. I was also going to mention that. Oh,
Rule of thumb for delta mu sub s, maximum delta mu sub s, is it 10%?
So the question is, what is a good rule of thumb for the amount that you can perturb before things fall apart?
yeah. So we have some working knowledge of that. So it's more empirically determined. It was about plus or minus 30%. Yeah. With mu a lot larger, like 4 times. Yeah. Yeah, you're not changing, but scattering for sure. Yeah.
But it also depends on the physical size of the perturbation. If you perturb everywhere, then the amount that you can perturb goes down. If you perturb in a small place.
That's good. Yeah, I'm glad you remembered that. Okay. Yeah, so I was wondering if anyone is doing SFDI. Anyone? Because there's somebody from Darren's group, but I don't think they're doing SFDI.
But yeah, someone else.
Okay. Okay. Well, all right. Well, in a spatial frequency domain, they illuminate the surface of the tissue with these sinusoidal, and usually it's along the x-axis. So you see these sinusoidal bands, and if you'll see it when SFD day is here. When you look down, it kind of just looks like lines of darkness and lightness going along. They're actually sinusoidals. And you illuminate the surface with this source, and then the light goes through, scatters about, absorbs, comes back out. And what gets measured by typically a camera is that the amplitude has attenuated and the phase has shifted. And because of that, then they can tell information about the subsurface characteristics of the tissue. So how do we do this in Monte Carlo? This roadmap comes in, but there's a little bit of a difference. We take the integral differential equation for the radiance, and we Fourier transform it with respect to x and y. So now we have a radiance with respect to z. We have this fx, fy vector here. Put hats on everything because we're in Fourier space. Omega is the same. And we follow this roadmap where we change this integral differential equation to an integral equation. We change, we make the equivalent probability model. And that's how we create an estimator in Monte Carlo for SFT. So some of the details here, we start with the time-independent RTE. And we do a Fourier transform over transfers x and y. So you'll now notice that this omega used to be a vector. Now it's just a scalar, omega z. This used to be grad, a dot here, where now this is just the derivative with respect to z. And the key difference is something I show in red here. Okay, so, and this is showing what in Fourier space, what this L term is. Okay, so now we have the integral form. Again, same sort of thing. Think method of characteristics. There's an integrating factor. Solve the ODE. You get an equation that looks like this, where the fancy K now has this term in here, and S has this term that came from the previous chart. Okay, so let's do something easy like analog, where we're spelling out what the ratios are in an easy way. But these ratios, because of that extra term in red, are going to have a form that looks like e to the minus 2 pi I spatial frequency, distance traveled from x location, because we're illuminating with sinusoidals along the x, where the photon pops out, and the difference between the source where it was injected. And you do that for every collision, and got that pseudo collision, such that, let's just say it's homogeneous. You run the photon, it comes out, you say, it came out at xk superscript 1, this value here. It's this distance from the source. And now I just apply this 2 pi I, whatever spatial frequency I'm interested in, and say, that's my photon weight. Now what actually gets, this is a complex estimator, what actually gets tallied is the real part and the imaginary part separately. Means of those are generated. And then at the end, you combine them to get amplitude or phase. So this is something of a shortcut method. See if before this method, I think I didn't give reference. So Adam Gardner came up with this method. He was a graduate student in Boston's lab. And prior to the establishment of this method, people would run spatially resolved reflectance and discrete Fourier transform that to get the spatial frequency domain result. There's discretization problems with that, aliasing problems. So that's what motivated Adam and Boston to work out the details of how you would run a Monte Carlo simulation and get the appropriate weight of the photons to tally. Next, we're shifting to temporal frequency, FDPM. Anyone doing FDPM? No. Okay, well, I'll go quickly. So here we're putting in sinusoidally, the amplitude is sinusoidally modulated. Okay, so, and then we detect at a location after the photons have gone through here, and the change to the amplitude, reduction in amplitude, phase change
Modulation is in time as opposed to space.
Yes. Did I say that wrong? Okay. Yes, it's with it. There's a time here on this axis. Modulations with respect to time. So we take the time-dependent radiance equation, Fourier transform that with respect to time. So now we have hatted functions here. This is temporal frequency now in Fourier space. And we go through the same process. We do the, method of characteristics, get this estimated. We have a detector. And so let's just look at what the result is. So here's the time dependent, transform it with respect to time. We get these red different values here. That's the key term. Testorf called this the shortcut method because he was driven by the same reason Adam was, is that you could Fourier transform reflectance versus time after the fact, but you get problems with that. So he said, let's just get it directly, and came up with this method back in '99. And so yeah, these are the components. I'm just showing what's different in red, the integral equation. And then the way that you estimate, after you put it into the analog and a bunch of things cancel, just like spatial frequency, you end up with a tallying weight of e to the minus 2 pi temporal frequency times the time the photon spent in the tissue prior to detection. That time is calculated from the distance traveled by dividing the distance traveled by the speed of light divided by the refractive index of the tissue. And you're able to put that in here. Again, you can account, tally for whatever temporal frequencies you're interested in. And this is the tally that you sum up, divide by the number launched, and that gives you an estimate of the real and imaginary, put them together, get the amplitude and phase shift. Okay, so I think somebody's doing fluorescence though. Okay, a few more people. Okay, so I added this chart, first time showing it, so hopefully no errors, but could be. Just give you a general overview of how you use Monte Carlo to solve a fluorescence problem. So it consists of running a simulation for the excitation and then running multiple simulations depending on the emission wavelengths for the emission part of the problem. So first half, you have this excitation source based on some sort of wavelength. I call it excitation wavelength here. You have an area here which is the fluorescent region. You maybe have some fluorophore in there. And you run a simulation in which you capture absorbed energy in this region. Note that the mu A in this region is the native mu A due to the optical properties at this wavelength, but you're going to add in the mu A due to the fluorophore. Okay, so this total mu A in here, when you run that simulation, is the native plus the fluorophore. So you run that simulation, you determine absorbed energy in here. Okay, and then the second half is, and this equation is showing how you kind of combine the two. I'll just describe what happens in the second. That absorbed energy is going to create a fluorescence that's going to come out isotropically. Okay, so that's what I'm trying to show here with these red arrows, and that this volume, and it's a bulk thing. So throughout that whole volume, photons are getting initiated isotropically, and then we run the transport until they come out the surface where there's some sort of emission detector. So what I've described here in equation is that the emitted fluorescence at this emission wavelength, EMI, at a position R on the surface of the tissue is some power factor of the excitation power. You're going to integrate the absorbed energy in this volume right here You can integrate over all locations in that volume, the absorbed energy times I just threw everything into a constant Y. And this is the surface fluorescence this is the fluorescent photons that emanate from all these possible R's in here, positions in here, and are detected at the surface location. Okay, and this Y are a bunch of constants. There's things like quantum yield in there, the ratio of the UA fluorophore excitation UA to the total is in there, change of watts from emission to excitation. There's why I threw them all in here is that actually all those constants can be applied after the uniting of these two, the excitation with the emission simulation. Okay, but that's just one. Oh, and I should mention that this equation is coming from this handbook of biomedical fluorescence, chapter 3. Jacques wrote the chapter and described how you would do it in a Monte Carlo sense.
Maybe we should just pause for, make sure everyone follows this equation. Any questions on this equation?
Maybe I'll keep on going. Maybe there'll be more questions.
So Carol, just a quick clarification, right? The first phi is the distribution of fluence,
Mhm.
right? Throughout the medium at the excitation wavelength. But I guess R prime refers to all of the locations
Yeah,
in the fluorescent
because we're
domain.
integrating DV here.
Right, and that DV is
DV.
the fluorescent region.
Yeah, so you're only
Right.
integrating over that volume.
Whereas the emission is at a different wavelength, whatever wavelength of emission you're worried about. So you're using different optical properties for the phi emission because you're looking at a different wavelength for the emission.
Yeah, and if you have several, if you're emitting over a band,
That's the next line.
yeah, that's the next thing. So, say you have some sort of fluorophore spectra here, but we're emitting over band 800 to 900, then what I, in a kind of similar problem, I ran simulations at emission wavelengths 800, 810, 820 up to 900. Okay. And you use the value of the spectra at that wavelength, multiply the results of that equation I showed in the previous slide, multiply it by this value, and then delta lambda. So we're going to create an integral here, kind of like Scott, a continuous integral over this band that we have selected of emission, but you have to normalize it by the total area under the whole spectra here. So that's how we integrate all of our emission simulation results together to form a single result. Yep.
I just didn't quite get what was the phi emission on the previous slide.
Okay, yeah.
The detected surface fluorescence.
So so are you worried about this problem?
Yeah.
Yeah, okay, so it's actually Lawson and I had a discussion about this last night. When Steve Jacques wrote this, pretty much they were capturing everything coming out the top, like maybe some camera is set up and all fluorescence is coming out. I described it as I did with a detector because in the particular problem that I was working on, there was actually an endoscope detector that was capturing the fluorescence. And so it had a very distinct spatial area and very narrow NA. And so that's why I described it as the detected surface fluorescence. So yeah, but if you were like if you're just taking a camera, then it would be everything. Yeah. Sure.
Other questions? Okay.
Okay, so I'm going to now talk about easy stuff, the software and how it's organized, how you could potentially use it if you were interested for a problem that you're interested in analyzing with Monte Carlo. We have a library called the VTS, and inside is conventional Monte Carlo software. We have several ways to interface with this software, kind of coming from, yeah, I want to learn, but I don't really want to get too involved. We have a panel on our GUI that allows you to just point and click and do things, run a simulation. If you know MATLAB, we have a MATLAB interop where you can set up commands with MATLAB. We have oodles of examples in the MATLAB download of how to do a variety of different problems. And then if you really wanted to get your hands in and have the fullest capabilities, so each one is going to have less capabilities as you go down here. Monte Carlo command line is going to have everything, all our sources, all our tissues, all our detectors. And I wanted to mention, because I'm having fun with this, is that we're writing Python scripts now to use our software. And we have about 9 scripts written in Jupyter Notebook, but also command line that run simulations. And I think actually Scott was our first, I think he was our first user who put up his Python script for everyone's use.
Here, some of you guys use Python. Okay. Oh, good. As opposed to MATLAB. How many use MATLAB? Okay, you use MATLAB and Python. Okay, very good.
But
Okay, good to know.
Python's free.
Yes, I know.
I mean, we're all, everyone's on campuses, so that helps. But when you're not on campus, then MATLAB is ridiculously expensive. Okay, so we have in our GitHub site, which is where we host our software, we have a page dedicated to a wiki page. There's tabs and it's called wiki, dedicated to Monte Carlo. On the right-hand side, we have oodles of documentation, including how to download the software. I give the steps of how to get to the download. We have sample in files with that download, and we have directions on how to get those sample in files. And then we have different tabs on how to run the software, what sources and tissue definition detectors. And I just need to say that it runs on Linux, Mac OS, and Windows. So that's nice. So just the sources we have, so Jonica and David Kucha got together and made oodles of sources that hopefully describe most of the optical situations that you might come across. If you don't, then please let us know and we'll create an issue and create it for you. But looking down on the surface of the tissue, we have points, lines, circles, ellipses. You can start something from a picture, a JPEG, rectangles, a Gaussian decay of these shapes. And then from a side view, we have diverging sources, ones that diverge and go at an angle. We have converging sources. We have immersed, like say you had an interlipid and you're putting a fiber in there, submersed fiber here with different efficiencies on the side and bottom. And then we have surface sources. So these are sources that are emanating photons from the surface of these shapes, and the bulk sources where this is what we use for fluorescence, where they're emanating from the inside throughout this volume. And Jonica has written up a nice PDF that describes all of these and the particular how you designate in the M file, like spelling out this cone and then rotating it. For tissues, we have layers. You can embed a sphere, an ellipsoid, rectangular cube. You can infinite cylinder going into the page, which and we have concentric infinite cylinders that go into the page. A lot of biological, simplified biological systems can be modeled by a cylinder going through. Sometimes phantoms are designed that way with some sort of flow going. And most of the types have ability to have refractive index mismatch happening between, say, the outer and inner. Okay, then we have detectors, and in cylindrical coordinates, I want to kind of go over this because it comes up in the lab. Cylindrical, you can use cylindrical coordinates if the system is cylindrical. So if you have a homogeneous tissue, or you have, and the source is directed with symmetry, you know, it's not angled, and layers work. You could even have a sphere, but it has to be directly below the source, a point source, and so there's symmetry. Then you can capture all the photons coming out these concentric rings. So the area between these two concentric rings provides, once you capture all the photons, a lot more efficient, capture all the photons, divide by the surface area of this ring, you get a normalized estimate of reflectance at the midpoint right here. Okay, so that's cylindrical. And then we have, of course, Cartesian, but when you're looking side view in cylindrical, you have this center cylinder, and then you have these outer cylinders with, you know, increasing rho, and they're all normalized by the volume, but just know that, you know, there's a center one, and then each volume is getting bigger. Another thing that comes up in radians. So in radians, it's a function of theta and phi. And potentially you want to bin theta and phi and get a radiance as a function of those values too. Just to keep with theta, so positive z is into the tissue, so down, and theta is taken with respect to that. So you're not seeing me. So theta is down. Theta from 0 to pi over 2 is this lower hemisphere, and theta from pi over 2 to pi is this upper hemisphere. So if you were looking at the photons in a downward motion, then it would be in this bin of theta from 0 to pi over 2. If you were looking at the photons in an upward motion, it would be in the bin of theta pi over 2 to pi. And we also have, if you wanted to play around with perturbation differential Monte Carlo, we have detectors to play around with that. This is kind of what it looks like when you run the command line. Once you run it, we have a script in MATLAB to plot the results. In our, well, let Lisa talk about the Python, how it's plotted. I just list the software, I mean the units here in our software, just so you, when you're using the GUI, you know that time is nanoseconds. Everything else is millimeters or inverse millimeters. Our temporal frequency is in gigahertz, and wavelengths in nanometers. So I wanted to cover this because I think people who use the GUI think, wow, I'm getting Monte Carlo results, and you are. Because of real-time results, but they're using something called scaled Monte Carlo. And it's a different part of the library. We have MATLAB Interop that uses it. The GUI you'll see in the forward and inverse panels are using it. And Keenly and Patterson back in '96 came up with a way in which you run a simulation, and they ran it with these optical properties given on this line, ran a simulation, and they captured reflectance versus source detector separation and time. Okay, so from that, so they have this big result, and then somebody comes in and they figured out the equations that say, you know, I don't want mu A to be this, I want it to be this value and mu S to be this value instead. And they figured out how to pick the appropriate row and time bin for the new system, if you will. So everything's scaled to that new system. And so that's why the results are real time. You say, just apply these factors to this end result, and you can get the results for the different sets of mu A and mu S prime. That's very nice. Michele Martinelli, who was part of VP for a while, was using it, and he said, you know, in the very far row and time bins, there's not too many photons out there. And so the estimates are not so good. So he decided, let's do some adaptive binning where we put bigger bins out in the far times and far rows. And then he also used non-uniform rational B-splines. And so NURBS is what we call it. And so those two options, basic and NURBS, are scaled Monte Carlo options to plot results with. Just need to reiterate that these are not photon by photon results like in conventional Monte Carlo, but they give very nice results for homogeneous tissues. And you'll be using those in the lab.
Carol, may I expand a little bit on that?
Oh, sure,
So
sure,
going
sure.
back,
Go.
so I think it's really important for people to recognize that in a Monte Carlo, right, you have a detector, all detectors are a finite dimension. That is, they're collecting photons over some sort of finite spatial region and a certain temporal region, right? And so in scaled Monte Carlo, they're averaging all of the photons in that detector, and they apply the same scale factor to all of those photons in that virtual detector. And so, and therefore, you already have an intrinsic estimate. And even though the scaling is correct, the scaling is not exact, because if you want to do the scaling exactly, you should find out the exact time that that photon emitted and the exact location and apply the scaling on a photon by photon basis. But in these scaled Monte Carlos, you're not doing that. You're just applying a mean reweighting. And what happens is that your variance tends to degrade a bit more. So in that sense, it's not a rigorous Monte Carlo because you're not applying the reweighting on a photon by photon basis. So, a certain amount of care and caution should be used
But,
when
yeah.
using, but it's a very powerful tool and we use it throughout the course.
Yeah.
But I just wanted, just from the instructional point of view, people
Yeah.
should understand
And
that.
there's no scale for layers or inhomogeneities, so yet. So can't do that. Okay, so just my summary that hopefully I covered how you get these estimators, perturbation, differential, spatial and temporal frequency, even though not too many people doing that, and then how to run a simulation. I want to put myself out there. If you guys are interested, setting something up, please approach me and say, hey, can you show me how to do this? And I'd be happy to help you. Now, during the course and after, so. Sure.
So just to emphasize, in the afternoon, you're going to get some experience in
Yeah.
running some Monte Carlo simulations,
sure.
and hopefully those exercises will give you some insight into the tissue optics mechanisms. Any questions?
Can you go back to the detector slide, the MCCL detector? I was just a bit confused with this part. Is it because detectors can be different shapes? I'm just like not familiar with
Yes.
what the structure of a detector.
Yeah, so they are different shapes. So in this, I think that's what I was trying to describe here, is that we're actually capturing all photons in that ring, but we're assigning it to this distance in the midpoint. We're dividing by, so we capture all those photons, and then we divide by the surface area of that ring. And then, so yes, they can definitely.
So is that first one kind of like a camera sensor? Is
Well,
that what
if you
it
had a
is, or-
camera, you probably have some sort of pixelization of that camera. And so it would probably be more like this.
Mhm.
Yeah, where each pixel, so you want to know from each pixel, what is the reflected light?
Yeah.
Yeah, so you would use the Cartesian version
Okay.
of that. Yeah, and I've done, and you can define the pixels at the potentially same size as the resolution that you have. Yeah.
And then what are some examples of the other detector shapes?
Inside. What
Yeah,
is
because
that?
you know how the Cartesian is for like cameras with pixel,
Yeah,
but like what about the other ones? When would that be used?
like in here.
Yeah.
Yeah, okay, so inside, those detectors are what we call kind of virtual detectors because they're capturing, say, things like fluence or radiance, absorbed energy. Those are all the tallies that are done as the photons are moving through the tissue. So
Interested in physical detectors? Is that what I'm trying to understand. These are in some sense, these live in the computational world. So the question is, I think maybe you're asking what physical detectors these correspond to? Is that your question? Okay.
yeah, it's a virtual grid, if you will, to allow somebody running a simulation to determine, yeah, in a hopefully good way of if you were interested in the measurement of fluence at this point, then you would, either grid out in cylindrical or Cartesian coordinates and capture the fluence in that point or several points around it, several voxels around it.
But I
Yeah,
guess from a practical instrumentation point of view, you can imagine embedding a fiber inside your domain with a given numerical aperture.
Yeah.
And then you have a location in a particular space and you're looking only over a certain narrow range of angles. So you could specify it through the theta phi, you can define, well, I want to know what is the fluence arriving at this location, but only in this narrow set of cone angles by specifying the phi and theta elements. The cylindrical coordinates is just set up in situations where the system naturally has cylindrical symmetry, and then you can leverage all of the photons in that cylindrical ring, and it just becomes much more efficient. But in terms of a physical detector that may be a cylindrical ring, I'm not sure, I know there are axicons that certainly can send in light. You could also potentially put a detector on, and you could get axicon detectors, for instance.
Okay, because
That could
I've
do
only
that.
worked with cameras.
Yes.
So I understand the first one.
Yeah,
Mhm.
right.
and if you had a fiber, one way is you in a source here and a fiber here, you could actually create a circle there to be the detector, and run the simulation, and then anything that comes out that circle would be detected. But if your system allows it, it would be better if you created a ring of circles. And that's what that ring is, and capture everything out, and then divide by the area, because they're from the source, all equidistant and represent capturing.
As long as
photons.
your tissue is uniform over that.
As long as tissue has cylindrical symmetry, and your source does too. It's not angled or something.
No, Chief, do you have a question?
From what I understood from the previous question, can you restrict the angles
Yes.
of capture?
Yeah, for sure, for sure. You can define your theta and phi bins as finely as you want. There's a trade-off. Adam found this out in another paper he wrote. You want your bins to capture the anisotropy of the field well enough, but making them too fine means that your tallies, your variance is going to be larger in each bin. So there's this kind of got to play around with a couple of definitions before you find kind of that sweet spot.
Thank you.
Thanks, Carol.
Sure.
A similar question. Do you mind to go one slide backward?
Sure. This way.
Yeah. So what are the shapes of a tissue?
So the tissue, good question. So the tissue is regarded as kind of a semi-infinite. However, so there's air above the tissue and then air below, although I usually make the tissue thick enough that it represents a semi-infinite. I also sometimes keep track of what comes out the bottom if I'm worried that I'm losing photons that could have come back up. But a lot of times it's infinite laterally. And that can.
It doesn't happen, right? You can actually put in inches and look at the leakage outside.
You could, you have to, what I've done is put an infinite absorber around a domain. I was actually modeling a phantom that had an infinite absorber. So I put an infinite absorber around the domain that captures all the photons. So that's possible if that's in your system. But you don't want to get rid of photons that just, like if If it's not part of the system, then you want to make sure they have the chance to tally if possible.
So if I choose the like option to be ellipsoid, am I simulating a tissue that overall has a ellipsoid shape, or like how's that? How do I interpret that?
How-
Shapes.
These shapes?
Yeah.
Yeah, so we have different tissue definitions. So we have a single inclusion tissue, which allows you to include an ellipsoid, voxel, or cylinder. And by defining that in the in file, you would find and it has to, the one caveat is that each of these shapes has to lie inside a layer. They can't straddle layers. So you might have different layers up above and different layers, but the sphere or ellipsoid has to be completely inside one layer. And then you would spell out like the location, the center, the dimensions in each, if it's, yeah.
So those shapes are actually the boundary of your of the volume that you're
No, these
evaluating.
are actually places to put different optical properties.
Oh,
That's a
okay.
good question. Yeah.
Okay.
Yeah. These, so say you have some sort of sphere ellipsoid where maybe there's a tumor or somewhere where I use this for a vessel a lot physiologically, where there's some sort of change to optical properties in there. And I actually have a concentric cylinder that has different optical properties, like it has a skin.
Okay.
Yeah. So yeah, it's just a way so that every time you have a blue line, you're going to change optical properties. And yeah.
Okay, got it.
Yeah.
So for example, to evaluate that inverse problem, say you have a delta in the measured intensity, how do you understand what's happening inside? You can put a virtual
Yeah.
shape and change the property,
Yeah.
something like that. Okay,
For sure.
got it. Thanks.
Just a question about the code implementation. So does this run on CPUs, or do you use graphic cards perhaps to do parallel processing and speed up calculations?
We have parallel processing.
Okay.
We have parallel processing involved. There's actually documentation on our parallel processing. We've done some studies, and I'm not sure, each computer we have found is like I have a desktop in Engineering Tower that has an optimization in the hardware. And when I ran parallel, it was kind of fighting it because it was kind of figuring out, oh, she's doing this loop, I can spread it. And it would spread it over CPUs. And then I said, no, but I want you to use these CPUs.
Yeah.
And so we ran some studies, and so it's kind of hardware dependent on what the sweet spot on how many CPUs you should choose to run. Yeah.
Mhm.
Yeah. But we see one of the key things about running in parallel is that you want to make sure that each of the simulations on each of the CPUs are seated appropriately so that you can add them back together. Because if they're not, then they're not uncorrelated results. Yeah.
That being said, I just want to provide an editorial in the sense that there are many Monte Carlo engines out there that are open source, that are developed. Our goal hasn't been to actually make the fastest Monte Carlo simulation out there. And there are many other packages that are much faster than ours. Ours, I think our philosophy has been, number one, we want to make sure that all the solutions we provide within the core conventional Monte Carlo engine, that the solutions are traceable to providing rigorous RTE solutions. That's one of the reasons why we haven't done fully voxelized, because to do that very carefully actually requires computation very carefully at every single interface. The other thing that we've emphasized is to provide different types of estimators, because typically most engines out there only provide a single estimator. And the other thing that we've tried to emphasize is to provide lots of options in terms of sources and types of detectors. So there are always trade-offs, it's also part of where our power stroke is. But there are other great engines out there. And I know that like Chin Feng's engine. In terms of if you want speed, you probably want to use Chin's code, MCX. But you also need to, and also we provide lie detector. So we give native results in the spatial frequency domain, temporal frequency domain, and these other codes I don't think necessarily have those sorts of flexibility. So, yeah. Any other questions?
Hi, I'm not too familiar with like the development of different Monte Carlo simulations, but has there been work on like scatterers that are moving or like media that is moving and dynamically changing?
Has there been work doing Monte Carlo simulations of media that's moving?
Yeah, or like changing.
Yeah,
evolving over time?
that's a good question. In and probably Vasan's probably better at answering this, but because I have not personally worked on that. I've only taken snapshots of a situation and then moved it through. However, I worked with Caitlin Reagan in Bernard's group, who we actually have estimators and code to handle speckle. Yeah, and even Tyler Rice was part of the group at the time. He wrote another solution to that using our code. So there are aspects of it, but for instance, if you were talking something generally like, having something like blood flowing through a particular cylinder, and does our code handle that? No. Yeah. But I can point you to Caitlin's speckle if you are interested. Yeah. Okay, Vasan's gone. We're done.